So good evening to everyone. I'm Karen Day, the Dean of Science here at the University of Melbourne. Before we begin this evening, I'd like to pay my respects to the traditional owners of the land, and I pay my respect to their elders past and present. So thank you for joining us tonight. Tonight's lecture is just one of the many events that are on for the Science Festival, part of National Science Week. I'll put in a particular plug for one of my favourites, a project that I've been very much involved in. It's Blood, part exhibition, part experiment, and this is a pop-up gallery bringing art and science together. So it'll be an interesting one to look at. It's not just a medical view of blood, but some very interesting ideas. So if you're feeling creative and want to be challenged, go and have a look at that. So tonight our lecture on the Anthropocene is going to be presented by Associate Professor Mark Quigley from the School of Earth Sciences. I'll give you some details on Mark's history. He completed a Bachelor of Science Honours at the University of Toronto, a Master of Science at the University of New Mexico, and a PhD here at Melbourne. He's published more than 70 research articles on his research conducted across 5 different continents. He's supervised more than 30 postgraduate students and is a leading editor of Geologic, the most prestigious journal in the geosciences. Mark's research bridges geology, seismology and engineering. He studies the geologic and geomorphic evidence of past earthquakes to understand the timing, magnitudes and the dynamics of seismogenic fault rupture, and forecast the locations and timing of future earthquakes and their effects. These data are important for defining seismic hazard, informing land use planning decisions, and developing robust building codes. He's currently working with Geoscience Australia and engineering companies to better characterise Australian seismic hazards at sites of key national interest. Importantly for you tonight, Mark has a passion for science communication and has received awards for this work, notably the prestigious Geological Society of America Public Service Award and the New Zealand Prime Minister's Science Communication Prize for his efforts in communicating the 2010 to 2011 Canterbury earthquake sequence to the citizens of New Zealand. Mark's recent research includes the study of human influence on earthquake hazards. Last year, he and his students published work that showed that the relationship between anthropogenic deforestation and increased travel distances of seismically triggered rockfalls. His talk tonight will feature some of this work. So please join me in welcoming Mark to the lecture. Thank you, Mark.
Thanks very much, Karen. And thanks very much for coming. It's great to have you here. It's great that you're supporting the Science Festival. It's a really awesome event. I'm just trying to get the lighting right here. Daryl, do you want to give me a hand with this, perhaps, so that people can see? Thanks. I'll start like this. So the Anthropocene, it's this thing that absolutely fascinates us. It's so interesting to us. There's a narcissistic element to it. We want to know what our layer is going to look like 1 million years from now. There's fear. Are we really doing things to change the behavior of Earth? Thanks very much, man. That's good. There's this kind of legacy issue. What are we leaving for our children and their children? And how do we possibly characterize this? And then there's this ethical issue of our time on Earth. We've been here for but a blink of an eye. Is it ethical for us to, I'm doing this magically. Is it ethical for us to engineer our planet and to have such a strong influence? And so the Anthropocene, this massive thing, has absolutely captivated us. And I'm going to give you some information tonight about my perspective on the Anthropocene and the global perspective on the Anthropocene, but it is absolutely a massive talk. So there's not going to be everything covered, but we'll do our best. I want to start with a quote from 1873. It's translated from Italian. I recall with pleasure the event that we believe opened the vulgar era, the Anthropocene era. We have this idea that this is kind of a novel concept, something that has arisen over the last, say, 20 years of research. But in this document, he refers to this creature. I think he means us. This creature, absolutely new in itself, is to the physical world a new element, a new telluric force that for its strength and universality does not pale in the face of the greatest forces of the globe. How profound. He even mentions the geologists. He talks about some of us, the future geologists, wishing to study our epoch's geology would end up narrating the history of human intelligence. And actually, it's quite an interesting comment, and it's not exactly something that we cannot easily characterize, but we can see our elements of our human record passed down through time, extending back millions of years. So if we think on the time scale of, say, millions to hundreds of thousands of years, we find evidence of, say, quartzite hand axes in the geologic record. In Australia, we can see evidence of 20,000-year-old footprints, or Aboriginal people walking across swamps and lakes in Central Australia that were then buried by sand. And we can see evidence for Aboriginal hearths unearthed recently in archaeological investigations. And then we can see this Roman stratigraphy. Rome built layer upon layer of discarded past civilizations extending back from the Bronze and the Iron Age up into the present. So this is, at some level, some people's perception of the Anthropocene, a lot of human artifacts left through time. And then there is this less glamorous Anthropocene that actually I encounter every day on my bicycle ride from East Brunswick into work. The Anthropocene that's exposed along Mary Creek in East Brunswick, and I call it the Golden Spike, basically this boundary between Holocene hill slope sediments here and human garbage, plastic and bricks and fill that overlies it here. And so for me, this is actually the type section of the Anthropocene in Melbourne. It's kind of this clear boundary layer between the stuff before we started leaving permanent markers in the geologic record. And we can see this process actually going on all the time. In fact, if you walk along any of Melbourne's creeks, you can see plastic bags strewn through the trees that eventually get worked into plastic-laden deposits along the creek beds, like you can see here. So this is geology in action, and this is the Anthropocene. Since Stopani's initial concepts, there were some real classic studies done. Man as a geological agent in 1922, and a kind of seminal paper, Geology of Mankind, and another one called the Anthropocene. And since then, this concept of the Anthropocene has actually absolutely exploded. It's a fractal, like branches of a tree. It's a fractal explosion, and it's hierarchical. Stemming from these papers, we now have a rate of almost 1,000 research papers per year published on the Anthropocene as a concept, with this massive surge in the mid-2005 and so on up into now. So Anthropocene science has totally exploded, and by the company that we have here tonight, it's obviously of interest to some. We've contributed a little bit to this. We've studied rockfalls. We've compared prehistoric rockfalls with Anthropocene rockfalls. And then Professor Caroli, who's in the audience, has also worked with his team looking at anthropogenic contributions to climate and weather. And so we, at the University of Melbourne, we actually dabble, more than dabble, we actually tackle these challenges in our own way. Of course, some of you might think of the Anthropocene completely different. You might think of bugs, you might think of death, you might think of plastics. And I've just given you an example of some people's concept of the Anthropocene here, showing, for instance, things like the increase in fossil fuels and landfills in the sort of 1950s, our development of antibiotics and our gradual resistance to them, vaccinations, all sorts of things. And in actually going back further in time, things like megafaunal extinctions and so on. For some people, this is the concept of the Anthropocene. The rise in plastic production on Earth over since the 1950s is some people's version. And the extinction, we're actually tracking towards extinction rates that are on par with some of the greatest extinctions that we've had, these geologic boundaries in past. So we have a variety of concepts here that contribute to our idea of the Anthropocene. And if we want to think, again, in its broadest sense, some of the things that people talk about when they talk about the Anthropocene, you can see just a whole myriad of different types of proxies for what we might consider the new age. So carbon dioxide and nitrous oxide, methane in terms of gases, ocean acidification, primary energy use, fertilizer consumption, all these things that we do as humans and how it impacts our Earth. And so this is quite profound, and there's lots of richness in this data as well. So all this fear and all these things that we're doing, how do we deal with it? And I think it's something that I do not want to leave you tonight here with a negative view of our future, because I don't believe that is so. I think that what I want to leave you with is this transition that we're in the midst of, that's happening now, this optimistic Anthropocene. And this is this transition to stewardship of our planet. So we were pretty good at doing lots of stuff, and then we got better at understanding what the effects of the stuff we were doing were having, and now we're crossing into, hopefully, this idea that we're becoming more successful stewards, more efficient stewards of our planet. I want to talk about three main things tonight. I want to talk about humans in the context of geologic time. I want to talk about geologic manifestations of anthropogenic processes, and I want to compare these with pre-anthropogenic rates. And I want to talk about anthropogenic influences on geologic processes. So are we actually doing things geologically? Are we actually meddling to the degree that we're influencing the way our Earth works? I'm going to emphasize some Australian stuff, but I want to make sure that we keep a global perspective, because this is, of course, a global problem. So we'll start with humans in the context of geologic time. This geologic time scale, this is a beautiful model. It represents more than a century of research by thousands and thousands of scientists from around the world. And it is a model. Let's not mistake it for anything other than that. It is a model of Earth time, beginning at 4.6 billion years ago and coming to present. Like any model, it's wrong, but it's less wrong than a lot of other models, and it is constantly revised. It becomes increasingly precise with time, which is quite a beautiful thing, and some of these boundaries between geologic periods and epochs are actually incredibly precisely defined. The stratigraphy of rocks reveals biologic changes, changes in lithology, chemical changes, magnetic changes, astrophysical changes in the tilt and the wobble and orbital cycles of Earth, that are dated by geochronologic techniques. And really, the way I look at this model of Earth time is that we have these periods of dynamic equilibrium that get punctuated with calamity and also opportunity. So mass extinctions followed by explosions of life, for instance. Some of the more notable things in our early history, we're now at the stage now where we think we're finding fairly convincing evidence that life was on our planet as long as 4 billion years ago. We're finding evidence of biogenic graphite and zircons and evidence for bacterial life. So that's quite exceptional to think of 4 billion years of life on Earth. And of course, my own personal interest, we're also finding rocks that somehow have remained brittle enough to preserve records of earthquakes that occurred more than 2 billion years ago. Most of that material gets recycled, but some of it is still there. So that's quite cool. These golden spikes and calamities, of course, the most famous one is the KT boundary, which we now refer to as the KPG. It's not quite as, doesn't have quite as nice of a ring, but the Cretaceous-Paleogene boundary when the dinosaurs went extinct. And we can put our finger on this boundary in lucky places on the planet. And we can see, actually, that it's marked by big anomalies in things like iridium here. You can see at that boundary there, shocked quartz and tectites and chromium anomalies that have been interpreted as a giant meteorite impact. So mass extinction of Mesozoic species, including all dinosaurs. We have our own event horizon. We have our own geochemical footprint on Earth, and that is when we started doing nuclear testing in a variety of places around the world, beginning in the late 40s and continuing through into the late 50s. And so if you look at the global record of cesium and plutonium, for instance, you can see our own spike here where we have that record. And Australia actually contributes a small amount to that record. If we look at profiles through lake sediments in Lake Victoria and Gippsland Lakes, we can see these spikes in cesium and plutonium as well that correspond to the dispersion of these elements. There's a lot of ways in which you can try and capture the vastness of geologic time. And I think one of the most effective ways that I could think of, being in Melbourne, being the time of year that the finals are approaching, is to think about Homo sapiens in the context of a footy field. How much of that field have we actually been on the planet? And when you do the calculations and you think from goalpost to goalpost represents Earth's time, we are one very small step for man and woman on the field of Earth history. We're 5 to 11 millimeters. So we're basically less than 1/5 of the boundary line we've been on the planet, which is quite amazing when you think we have so much of that field in front of us, that we are such a small line. And then I had a bit of fun because I put T-Rex on the field as well. I put him right out in front. And it turns out that T-Rex just came onto the field 8.2 meters out. So he was in the goal square, and he went extinct 2.3 meters out, and he was straight in front. So how could they miss? They did 2.3 meters ago. In that millimeter of time, we have achieved so much in terms of our impact on the planet. If we look at, for instance, the land that has been used intensively by humans in the Holocene. So we could start with 8,000 years ago, and the red areas here are where we've used land intensively for agriculture, building cities, and so on. And we track our passage through time to AD 2000 now, and you can see that vast parts of the globe have been intensively used by us. If you look at just a snippet of one of those data sets that contributes to that idea, we can focus on New Zealand. This is Banks Peninsula near Christchurch, and you can see the yellow represents the area covered by forest, by native forest. Prior to Maori arrival, just prior to the Europeans did quite a good job at deforesting this particular area in the 1920s. But there's also something else that you can see there, and that is some of the yellow starting to come back. And that's one of the things I want to capture here. And we're seeing some of this transition to stewardship, which we really hope we can perhaps achieve on the planet. We have surging populations. Behind the text there, you can see population. We have surges in the amounts of dams. We've made lots of dams, and we've created new products that mark our presence in the geologic record and the rates of planetary change. So these are just some in teragrams here, the rise in plastics, in concrete, in synthetic fibers, things, aluminum, things that we can actually identify in the geologic record. So Daryl asked me before my talk, what are we going to look like in the geologic record? That's probably one of the main things that we'll leave: aluminum, concrete, plastics, and synthetic fibers. This idea of the Anthropocene, this Holocene-Anthropocene boundary, has been discussed a lot and debated in the literature. People propose different things. Megafaunal extinctions, perhaps that's the boundary. Perhaps it's when we had human niche construction, significant human niche construction, domestication of plants and animals. There's a variety of other different potential lower boundaries that people have proposed, and a variety of different ways that they propose them. But here's the thing. We're still, regardless of where you put this boundary, we're just a hair on the boundary line. That's all we are in the vastness of geologic time on our planet. And I find that concept, when I think about a hair lying on a footy field, about all that field, I think of that concept of actually being quite motivational. Because I think, ethically, what responsibility do I have to have completely changed the way that the world has operated for 4.6 billion years without some element of responsibility for ensuring that it has a good future? Okay, geologic manifestations of anthropogenic processes. in comparison with pre-Anthropocene rates. I want to have some fun with this. I did a bunch of calculations and came up with some really crazy observations. Yeah, I would love some of you to check my math for sure. But I'm quite interested in some of this stuff, so we'll talk through it. The Cambrian was this incredible time. This is an explosion of life 541 million years ago. And one of the main things in the geologic record we see is this diversification and sophistication of animal burrowing, including vertical burrowing, going down through the sediments. So these relatively simple burrows from the Ediacaran, the period of time before the Cambrian, gave way to these quite sophisticated burrowing systems here like this, including vertical burrowing. And why I find that kind of interesting is I think of us now as Melburnians, we're the great bioturbators. We're the ones who are doing, we're increasing the sophistication in how we burrow. So here's an example of the kind of tunneling machine that will be used to excavate the Melbourne Metro Rail project. In one of my courses, we're trying to predict just how much geology we're going to move as a result of that process and what we're going to find. But also, again, every day on my bicycle on the way into work, I can see evidence of vertical burrowing. We're actually doing a lot of this in Melbourne at the moment. We're excavating about 9 meters of rock and 2 meters of clay, and we're putting down vertical foundations to support our buildings like this. This is an example of one of these construction projects here. So we're doing permanent and irreversible changes to the geologic record. No matter what happens to us, as some sort of unexpected mass calamity, the rock that was intact there before is no longer. And so we're leaving evidence of our bioturbation. We're also, to take a line from the castle, we're digging holes. We're digging holes like Dale, big holes, in fact. This is an example of one of the holes in Brunswick where they're going to put a big shopping center here. The amount of rock moved out of that is absolutely incredible. Truckloads and truckloads. But actually, let's talk about the real big holes. Let's talk about the mines, the open pit mines. So this is a Kalgoorlie mine here, the super pit. It's 570 meters deep. And we excavate, we get deeper about 20 meters per year, although by the looks of it, I think we're running out of room to do that. 15 million tons of rock excavated every year to get 20,000 kilograms of gold. And then there's the biggest one of all. This is the Boddington gold copper mine in WA. 80 million tons of rock, which is the equivalent of the weight of 400 Eureka towers every year to get 22,000 kilograms of gold, which is 0.01% of the mass of the Eureka Tower, and 3,800 tons of copper, 18%. So that's a lot of Eureka Tower masses to move. And so I want to put that in some sort of broader context. When I looked at that photo of Kalgoorlie on Wikipedia, I thought, geez, I've seen something like that before that looks familiar in its scale. And then I realized where I was doing my master's research in the Grand Canyon, in the inner gorges. And when I did the numbers and looked at some topographic profiles across this, I found that actually the depth is not dissimilar. In fact, it's about the same. So the inner canyon of the Grand Canyon, the inner gorge of the Grand Canyon, is about the same depth as that. We actually have a pretty good idea of how fast the Grand Canyon has cut that inner gorge. And it turns out that the incision rate is about 0.5 to 1.5 millimeters per year, which is, as you can tell, just by looking at the numbers, is a lot slower than we excavated our big hole in Australia. And then the other thing we can do is think about if those rocks there hadn't been excavated, how fast would they erode? And we have some samples that tell us that. So an example of one of these is from the Darling Escarpment in Western Australia, where you have similar types of rocks and similar types of climate. And it turns out that those rocks only erode about 0.5 to 50 millimeters per 1,000 years. Okay, and to save you kind of doing conversions and stuff, I can tell you that the anthropogenic excavation of the Kalgoorlie super pit was 13,000 times faster than the Grand Canyon cuts down every year, and it's 400,000 times faster than that rock would erode if we were not there to help it erode. Now, the next thing we want to think about is where we send this stuff, and how much do we send? If we're doing these sort of big excavations around the country, how much rock does it add up to, and where does it go? We are the great geological exporter, one of the greatest geological exporters on Earth. We export 1.214 billion tons of rock from Australia each year. We export a lot of coal. We're the 5th largest coal producer and the largest coal exporter. and we export lots and lots of iron ore, right? So those two contribute a lot to our export mass. We used to send dust to New Zealand. Australia, actually, in the last glacial maximum was a lot drier. And we used to cast these big dust plumes out over New Zealand. And we've stopped doing that to some degree, although we still give them a little bit of dust. But now we send coal and we send iron ore to Asia, largely. So we've sort of replaced those processes. Just how much? Well, these numbers, when you start putting all the exponents in there, they seem like they get quite big and a little bit hard to comprehend. So I did some calculations of the volume of Mount Everest above the Tibetan Plateau, because I was kind of interested in that. And it turns out we send about 1 Mount Everest to Asia every 33 years. That's a lot of rock to go, to send away from Australia. That's not the total height, that's the height above the plateau there. And then if we take that amount of rock and we spread it all the way over Australia, we're going to send 1 centimeter of Australia over the whole continental landmass, 1 centimeter every 170 years if we continue at our current rate. So that's a lot. And if we look at the rate over millennial time scales, if we think that we might still be here in 1 million years, that's going to be 50 to 60 meters of Australia that's been sent to Asia, if we're still doing that. We can compare that to geologic rates of erosion in place. So the idea here is that we are looking at geologic erosion over the whole continent, and then we're looking at just the localized little excavations of rock that we spread out over the whole continent and comparing those things. And it turns out our little excavations are actually faster than the geologic rates of the whole continent. So we can compare them to erosion rates over millennia, and we can compare them to erosion rates over many hundreds of millions of years. And so localized mining removes rock more rapidly than the scale of erosion over our entire continent, which is really, I think, quite profound, yeah. The other things that we have, the other cool data set we have is how much sediment washes from our catchments all around the country out to the coast, where it ultimately enters the ocean. And there's been some really cool studies done, including this one by Wasson et al., where they looked at the pre-European yield, in this case in megatons per year, and compared that to the post-European yield in megatons per year. And that's really interesting because it shows this 2.3 times increase in the amount of sediment that erodes off Australia since we started doing stuff on the surface, like planting crops and ripping up trees and all that sort of thing. And depending on where you are, it can be 375 times faster. If you, for instance, took native grassland and woodland and turned it into a scalded or a gullied landscape, the erosion rates are incredibly faster than that. So just to summarize all this up, I think that Australia should try to get on the 2018 Biggest Loser, because if we look at the amount of pre-anthropogenic sediment flux to the ocean before we started doing stuff, 129 times 10 to the 6 tons per year. If we now look at how much we have the sediment flux, 302 times 10 to the 6, but we also add the amount of rock that we're sending offshore, which is a lot, it turns out that we're 11.8 times what our pre-anthropogenic rate was off the continent, either into the ocean or to other countries around the world to do as they will. I should point out that I have not calculated the weight of our imports, but from what I could tell, and I just had to do this really quickly, it seems from our import and exports that we seem to be trading rocks and gas for hopefully less dense students in petroleum. That seems to be the trade. I think it's working out quite well for us in that regard. So it's interesting. Okay, now to something I actually know something about. Anthropogenic influences on geologic processes. I'm primarily interested in earthquakes and their effects, but I'm going to talk about a few other things as well. One of the things that I get asked about all the time is human-induced earthquakes. And yes, we do make earthquakes. It's true. Believe it. The data that underpins this concept, this observation, is actually relatively quite simple. You count the number of earthquakes per year and the cumulative number of earthquakes in a given region, in this case the central and eastern U.S., and you notice big changes in earthquake rates, big spikes in recent times. Not so long ago, actually, there's a few little spikes there beginning in the 2005, 2010 range, and then a real surgence. And then you can compare that with the time in terms of the volume of the injection rate of saltwater disposal. These are deep water wells. So taking saltwater, salty brines that comes out of the Earth's crust when we, for instance, extract oil and gas, and pumping it back down in. And you know, those data speak for themselves. There's a bit of a lag time, but when you increase the amount of salt water that you dispose in deep wells, you get a seismogenic response to that. So the reason for that we understand quite well as well. If we think about faults having some sort of seismic cycle, they generate earthquakes quasi-regularly through time. The failure stress, this stress here at what time the fault ruptures, relates to the shear stresses that are acting on that fault and the stresses that are sort of holding everything together. We can think of that as the friction of the fault, and the normal stress that's clamping it together, and the pore fluid pressures. And if we kind of rearrange some things here, we basically need the shear stress acting on the fault, trying to get it to slip, to be equal to the coefficient of friction and the normal stress and the pore fluid pressures. And if we bump up the pore fluid pressures, what it means, the simple message, if we put more water into the faults, the shear stress required to get them to slip is lower. In other words, they slip at lower shear stress. Okay? This is a nice cartoon that just summarizes all the things that we do that create earthquakes. So we might inject fluids or extract fluids, and we might do it in the area of faults and then perturb stress fields around faults and cause earthquakes. Or we might pump fluids right into the fault planes themselves, and that's a good way of lubricating faults and getting earthquakes. We might remove lots of material from, say, for instance, some of the Kalgoorlie super pit sort of scenario that I mentioned. That perturbs stress fields and can decrease the normal stress on faults and cause them to rupture as well. Or we might do blasts, which create transient stresses on faults that cause them to rupture. We're pretty good at making earthquakes from other types of explosions, and nuclear testing, for instance, is a good way at perturbing faults and making earthquakes. We can create dams and reservoirs which load the crust and perturb stress fields and perhaps trigger earthquakes, but also pooling up lots of water in the crust allows water to percolate down into fault zones and, as I said, increase pore fluid pressures and drive earthquakes that way. There's even this idea that building really, really big, heavy buildings on top of faults can perturb stress fields enough to induce earthquakes. There's not a lot of research in that field, but it seems to be reasonable. So we think about this seismic cycle now. We modify it. We play around with it. We induce earthquakes on faults earlier than they might have occurred by, for instance, reducing the failure stress required. And really, I think about it this way. There is some sort of preordained order to the tectonic processes on Earth and the way in which one earthquake might trigger another. And once we start playing around with the dominoes, we kind of get unexpected effects going forward that make it even more difficult to tackle this as a scientific field in terms of forecasting and prediction. In Aussie, one of the more classic examples we have is this case of the Thompson Dam. So the Thompson Dam was built in Victoria starting in 1976 and through into the early 80s. And this shows where the dam was constructed there, damming up the river here. And as part of this goes on everywhere when we make big reservoirs, we actually monitor seismicity beforehand because we want to understand what's happening as we begin to play with the system. So this shows earthquakes color-coded by time and size-coded by magnitude in the area. And it's kind of diffuse patterns of earthquakes, not very many and not very big. And then the dam was completed in 1983, and the reservoir began to fill. And immediately below the reservoir, you can see this big cluster of earthquakes occurring at really shallow levels. So this is fluids seeping down from the reservoir and lubricating faults and popping off and lots of small earthquakes. But there's also something else that's interesting here, And that's an increase in the seismicity rate right below that, but at more seismogenic depths that are perhaps more important for triggering big earthquakes. And so that would have been a concern, I'm sure, if I was able to go back to that period in the time machine. And then ultimately, this eventuated in a magnitude 5 earthquake, which doesn't sound very big, but is enough in this part of the world to create strong shaking damage and be a significant earthquake. And when we look at that location of that earthquake and how the seismicity trickled down from the dam into that fault plane, we now interpret it as this fracture pathway below the reservoir allowed fluids to leak down into a tectonic fault that might have had an earthquake sometime in the future. We don't know 10,000 years, 100,000 years from now, but that fluid the things we did on the surface allowed fluids to get into that fault zone and actually trigger failure on the rupture. So quite a nice example of how science can inform that process. Anthropocene earthquakes. It seems now that we're focusing on how big can we make them through a variety of different processes. And people have argued for the magnitude 7.9 Wenchuan earthquake in 2008 in China actually could have been related to water reservoir impoundment. Not so convinced about that, but there seems to be a whole bunch of different ways in which we can induce large earthquakes, damaging earthquakes. So there's a lot of research going on this. By far, mining and reservoirs are the biggest contributor to the numbers of earthquakes, but certainly waste fluid injection and these sort of things are also really relevant, fracking and so on. This study I thought was really amazing because they argued that the withdrawal of water in an area of a fault actually perturbed the fault zone so much that when the earthquake occurred, the slip distribution of the fault was different than it would have been had we not sucked water out of the immediate area. They basically made this model where you deplete the water and you look at the stress perturbations. The red area has the highest stress perturbation, and they overlap that on their model for how the fault ruptured in the earthquake. And they argued that actually that because of the depleted aquifer there, you influence the stress this stage that you actually influence the slip distribution on the fault. So we're kind of getting a bit out there with that idea, but it seems to be kind of a cool, provocative concept. And then there's this thing that I'm kind of interested in is the engineering of earthquake ground ruptures. So something starting at 10 kilometers below our surface and rupturing up to the surface at 2 to 3 kilometers per second. Can we actually change the way it looks at the surface? And it seems like we can. We can see evidence for if we put big concrete bunkers on top of faults, not deliberately, mind you, but if it just so happens that there is one on a fault when an earthquake occurs, we can see the fault trace actually deflect around these rigid structures. And how that's just quite an interesting thing. And so people have played with it in a modeling perspective. They've made models where they've put big, heavy buildings on top of faults. This is particularly relevant to places like Tehran and Istanbul and Manila, where we know we have big, heavy buildings sitting on top of faults. And they showed that actually the fault deviated as it comes up to the surface as a result of the loading from the building. So it's this kind of idea that we can influence how those structures propagate to the surface, which is quite neat. My experience was that I mapped a fault rupture in New Zealand and noticed that actually where we had no fault rupture, if we had concrete bunkers, we actually created fractures that we wouldn't have had otherwise because the structures were rotating and breaking in the soil. After the Christchurch earthquake in 2011, we noticed that a lot of big boulders like these ones came down and went through people's houses and created a lot of problems. There are 5 fatalities of those earthquakes. And our idea was this seems sort of unprecedented because these rocks went into areas where we didn't have any geologic evidence for those big rocks. So we decided, well, not me, the royal we. I got my PhD student to do it. It was really painful. He mapped thousands and thousands of individual boulders with a GPS and took all the dimensions of them and locations and so on. But when he plotted the data up, it was just so cool. He found that the old rocks, the ancient rocks sitting on the landscape, only went this far. That is the furthest traveled boulders we could find. But the modern ones went, on average, sort of 200 meters further than any of their prehistoric predecessors. And the big question was, how could this be so? How is it that the modern rockfalls went further than any of their predecessors? I thought that the past was the key to the present. I mean, that's one of the underlying principles of geology. But our idea was that all the past rockfalls that occurred many thousands of years ago occurred when we had a native regenerating forest on the landscape. And the presence of this dense forest impeded the rocks from traveling as far as they would have. But we, of course, removed that forest over this time period, and so we were somewhat surprised that the boulders coming from those landscapes went further than they ever had before. One of the other things that we do quite frequently in earthquake-prone areas is build really heavy structures on top of sand that's subject to liquefaction. So when you shake water-saturated sediment, it changes its state. It loses its soil skeleton, collapses, and it flows like water. And so when we have really heavy structures like the footy stadium, this is the home of the champion Canterbury Crusaders, what used to be, not anymore. In the earthquake, the stand, there's a bunch of liquefaction that squirted out all around the stand that wouldn't have occurred otherwise if that structure had not been there. And we can even see it in this image here, which shows how much subsidence occurred in Christchurch through the earthquake sequence. And you can make that stand out beautifully just right there. This is an example of human-induced subsidence, human-induced sinking, putting heavy structures on top of ground that's subject to liquefaction. Of course, we're pretty good at also providing lots of avenues for liquefied material at depth to escape up to the surface. So this is an example here of a telephone pole that basically was like a conduit for a volcanic eruption of sand during the earthquakes. And the irony, one of the great ironies in this whole sequence is that if we looked at this is differential LiDAR through time, and if we look at the sinking, the gradual sinking of Christchurch City, parts of Christchurch, the red bits here, sunk up to 1 meter as a result of the earthquakes, went down. And the irony, of course, is there were big gravel-laden rivers to the north that would happily meander down into this new low ground and provide a source of gravel for us to rebuild our houses on. But we can't let that happen because people live there now, right? So we don't just let rivers run freely so much anymore. And the ironic thing, of course, is now we go out to that river, here it is here, and fill up big trucks full of gravel and bring it back into the city and lay it down in those areas to build them back up again. So in a way, we're doing Mother Nature's work for her. But the way in which we lay down the gravel is not the way that geologically that would happen. It's the cobbles aren't imbricated and those sort of things, but it's an interesting thing. A big story in human tectonics emerged a few years ago. People have always really known that if we suck lots of water out of basins, that the surface collapses. And this is another geological signal of the Anthropocene. And this just gives you an example of just how much subsidence. It's in feet, so I think we can work that out. So it's 7.3 feet, 3 meters or so of subsidence there. From 1965, that's where the land surface was, to 2013 in the San Joaquin Valley. And it was proposed that the amount of water that's been taken out of that basin is so much that it's actually unloading the crust, and the mountains around the basin are starting to get a little bit higher as a result of taking all that water out. So what they noticed was on the fringes of the basin, these are GPS vertical uplift rates, the uplift rates are really high around the edges of the basin. We seem to be seeing some sort of human-induced mountain building as a result of sucking water out of the ground. Fascinating. And then a few years ago, I gave a talk here at Melbourne about the Lucy Mud Volcano. This is really amazing. This is a human-induced mud volcano eruption. Well, it's still controversial, but I think the prevailing evidence is that we caused it. And this gives an example of the amount of mud that erupted, and I just put it onto Google Earth before. You can use the Google Earth historical imagery to look at the evolution of the mud from 2006 when it first erupted here to it eventually totally burying lots of houses in this whole area here. And the idea was that unsafe drilling allowed overpressured fluids under high pressure at depth to escape and transfer up through the fractured rocks and eventually erupt onto the surface. And it's still going. it's very difficult to stop a mud volcano from erupting, actually. And so even to now, you can notice subtle changes in that landscape. Okay, I've bombed you with heaps of stuff. I appreciate that. But it's an important topic, and it's a big topic. So I want to summarize with a few things. The Anthropocene is diachronous in its onset and its development, and it's totally diverse in its manifestation. It's controversial. People are still arguing about what it means. The earliest evidence of humans is 100,000 to even a million years before present. But there does seem to be this great global acceleration, including our marker horizon, our very own marker horizon with the plutonium and our plastic around the 1950s. There's no doubt that we've caused unique and irreversible imprints on the geologic record. So what are we going to look like? Yes, we will leave a record. In that narcissistic way, we will leave a record. Some of the elements are consistent with geologically preserved features that were used to distinguish periods of the geologic past. So there's perfect sort of scientific logic for this thing, for this Anthropocene thing. The rates and the dispersive nature of anthropogenic geologic processes like erosion and sediment transfer and rock transport greatly exceed the long-term average pre-Anthropocene rates. And we also have uniquely human dispersion patterns. Geologically, it's not very easy to send millions of tons of iron ore to the other side of the world without human intervention. Humans have significantly changed the locations and the rates and the characteristics of what we commonly perceive as natural phenomena. These include earthquakes and rock falls, liquefaction, subsidence, even perhaps mountain building and mud volcanism. And our geologic legacy will survive long after our extinction. Whether we go extinct, I'll leave that up to the audience to decide. But if we do, we will leave this record. And I want to finish with this. It's quite a beautiful passage of text, which I'll read to you from the Anthropocene. We are the first generation with widespread knowledge of how our activities influence the Earth system, and thus the first generation with the power and the responsibility to change our relationship with the planet. Responsible stewardship entails emulating nature in terms of resource use and waste transformation and recycling and the transformation of agricultural, energy, and transport systems. Effective planetary stewardship can be built around scientifically developed boundaries for critical Earth system processes that must be observed for the Earth system to remain within a Holocene-like state. An effective architecture of governance system for planetary stewardship is likely to be polycentric and multi-level, rather than centralized and hierarchical. In other words, we all need to buy in globally. So I want to return to this. This is the Holocene Anthropocene type section in Melbourne, and I want to show you what's on top. This is what's on top. This is our transition. Thank you. Are there any questions? Yeah, go ahead. I could. Yeah, it's a very difficult problem, and it's about what is scientific evidence and what is belief, right? I mean, that's really what it boils down to, what we have indisputable scientific evidence for and what we may choose to believe in. And I can believe in anything if I want. If I don't need to have it backed by real scientific evidence, I can believe in it. And there's a lot of real cultural value in people believing in things that may or may not exist. So it's very challenging. All I can say is that we need to do our best. And my experience has been actually for a lot of really good science-based decision-making in Australia and New Zealand. And so I don't think that we're descending into global madness where scientific evidence doesn't matter anymore. I don't have a doomsday kind of view of that. I think that in the US that might last for another year or two. In some instances, perhaps or perhaps not. But I can also assure you that there's plenty of big, science evidence-based decisions that are being undertaken in the US every day. So I'm not so concerned, and I think that we're going to be okay. Yeah. Yep.
I think it's really interesting the way we're now realising from our sciences like climate change, ontology, that one of the key problems is communicating really complex science.
Mm-hmm.
I'm not a biophysical scientist, but I'm lucky enough to work with biophysical scientists, paleoclimate scientists. So I found a lot of the graphs and charts and things. I was going, okay, I understand depth models and things like that, but I've had that privilege and that access.
Hmm.
Do you think there's a way that scientists can make some of this stuff a bit more accessible around your areas,
Mm-hmm.
the paleogeological area?
Of course, yeah, and I think we're doing it. The thing about the generation that a lot of you are in now is that everything is Googleable and everything is there, and so we should be increasing our presence, and we're doing it. We're doing our best. I mean, some of us are to provide more science, variety of levels. I mean, giving talks at primary schools, putting heaps of stuff on YouTube. This is a battle that can be won, I think. And I don't think we all need to be able to understand complex scientific graphs to have a functioning society. I mean, my wife is in performing arts, although she's pretty good at some of this stuff too. But she doesn't need to necessarily to do her job and make the world a better place. She doesn't need to necessarily understand log plots, but she should hopefully appreciate the value of science. And that's why we're here, is that, science is really critically important. So, yeah, I think that we can win that. Yeah. Yeah.
You'd like to make some predictions about the future of our food supply in this context?
That's straying way outside of my field of expertise, which has not stopped me before, but no. It's very complicated, and I think about it all the time because there's a lot of really effective work being done in a lot of videos and television shows about where our food comes from. And since moving from New Zealand back to Melbourne, I've often felt a little bit decoupled from that process. In a way, it's like we have 4 million people in Melbourne, and magically there's enough food that comes in to feed us all. Not only that, but we can go and get exotic fruits off-season in any supermarket we want. And it's just absolutely mind-blowing and amazing how that works. And I think from that perspective, this is a huge global thing. I don't know. I mean, I try to grow my own veggies at Ceres, but that doesn't seem to work all that well sometimes. And, it's just, yeah, without sounding like a buffoon, I think I'm going to leave it there. It's a huge problem. I don't know much about it other than it overwhelms me sometimes. Yeah. Oh, one more question? Yeah. Okay.
I wonder if you know anything about geoengineering studies about geoengineering our climate. Is that something that we can consider science fiction?
No, it's not. And there's someone in the room who can speak to that. So I'll pass that over to David if you don't mind. Yeah.
Good to know who your friends are, Mark.
Yeah.
So my name's David Caroli, and I work on climate science, and geoengineering is effectively a group of, if you like, approaches to trying to manipulate the climate through human interventions. There are 2 different types that are typically talked about. One is to enhance the removal of carbon dioxide from the atmosphere, which is really an acceleration of natural processes that remove carbon dioxide naturally, like just growing trees, photosynthesis. And then also also geological removal of carbon dioxide through mineralisation of carbon dioxide in rocks. That is less likely to be dangerous, although there is evidence that it can also be dangerous in exactly the same way that Mark's talked about, that injection of carbon dioxide as a liquid below the surface can in fact change the stress below the surface in fault zones, and there is evidence that injection of carbon dioxide below the surface can accelerate earthquakes already where it's been tested. So that's a link back to Mark. The other thing in terms of geoengineering is, most of the heating that we get on the Earth is from sunlight. So if we could magically, or through intentions, inject particles or do something to reflect more sunlight back out to space, change the amount of clouds, have injection of particles in the upper atmosphere, or through rockets put reflectors into space, maybe you could reduce the amount of sunlight that the Earth receives. Now there's lots of problems with that, and it is wacko science fiction. I sort of suggest that that is similar to what scientists tried to do when they tried to remove the cane beetles by importing cane toads into Queensland. This was to solve one problem with another intervention. Scientists did it, recommended it, and unfortunately it has had major adverse impacts in Australia for the last 50 years that will continue for at least the next 100 years or more until we work out how to get rid of them. Cane toads, which are marching towards Melbourne at a rapid rate.
Thanks, David. Thank you. Thank you. I think we better wrap it up there. So
it's my pleasure, Mark, to thank you very much for an excellent lecture this evening. I really like the optimism, the transition to stewardship, and the garden. Made me think of Voltaire's essay on optimism, Candide, and the bottom line there, you've got to look after your own garden. So, whenever I've had those moments where you think, oh my God, it's all going horribly wrong, you read that essay and you get the message. So, also to say the Faculty of Science is really investing a lot in thinking about Earth systems, environmental science, building up its expertise in plant science, and doing, I think, all the right things to train the next generation of scientists to hopefully do their best to tackle a number of the world's pressing problems. So thank you very much, Mark, and thank you all for coming along tonight. Thank you.
yeah, thank you.